Hey everyone, Merry Christmas, Happy Holidays, and all that. Um, so this is my second video where I'm working on this book, Relational Interpreters and miniKanren, working on draft 0. So the idea is I am going to use you, the audience at home, to take the place of the mythical graduate student or whoever that I want to teach or who wants to learn about relational interpreters. And, I'm going to work on the book as if I were sitting side by side with you and we were going through things like basics of scheme that you need to know. I'm not going to teach recursion, that type of thing, but maybe ML or Haskell or some functional programming, something like that. You're new to scheme though. Maybe you are a common Lisper. So we're gonna go through that, and I'm gonna try to pretend as if you're sitting next to me and you didn't know this stuff, and I'm gonna explain it to you. Try to come up with examples, and I've got Emacs open. So we can set it up like this. Actually, let's see, I'm going to switch sides. There we go. Let's find scheme. Here we go. Here's the scheme part. I'm just going to skip the aspect of how do you load Shea scheme, how do you install Shea scheme, how do you start a REPL. Also, like I said in the last video, I want people to feel comfortable with scheme and Racket. I'm not going to talk about how to install Racket or Dr. Racket or how to start Dr. Racket. I'll go back and fill in that part. That's not what I want to do. I want to avoid getting stuck, and I want to get into actually talking about the scheme language and coming up with examples and all that. So let's go to that chapter 1, and we'll just go through it. And this is sort of me giving an in-service like I used to give at the summer camp that I was involved in running. All right, enough scheme to get by. We need to know some scheme, since scheme is the host language for the faster miniKanren version of miniKanren we will be using. Faster miniKanren inherits schemely features such as cons pairs, quote, and letrec. We also need to know scheme because we will be writing interpreters for subsets of scheme. In particular, we need to feel comfortable with the evaluation rules for scheme, including the notions of expressions and values. And we need to know some scheme if we want to be able to read much of the miniKanren literature. Okay, really scheme and Racket. And then here's a side note or footnote that a reading knowledge of OCaml would also be helpful for reading the miniKanren literature that uses OCanren, a miniKanren-like language embedded in OCaml. Okay, there we go. So we've got a little prose here. I could punch it up. I could add some humor and jokes and drawings, who knows what, at some point. But I'm not going to do that now. I'm just going to try to get a draft going. Okay. I found it interesting to read about, how Doug Hofstadter wrote Gödel Escher Bach, which originally started as a long letter to a friend, and it grew. But it sounds like the first versions. The very first draft of that book, didn't have a lot of the fun things that we think of now. So I'm just at the point where this is more, think course notes, that type of thing, very functional. Okay. A few comments on scheme. All right. So this is about why scheme is interesting and worth learning maybe, or why we like using Scheme. Has a small core, it's compositional, a few exceptions to rules, very powerful, lots of ways to do metaprogramming, including the ability to extend the syntax of the language. Great for writing interpreters, compilers, and DSLs. Okay, that's fine. I can turn that into a paragraph. Okay, and then something here maybe about the Scheme reports, versions of Scheme and implementations of Scheme. That's one of the things, is that there's R5RS Scheme, R4, R6RS, there's Air5, there's R6RS small, R7RS small, R7RS large. R7RS large is still under development. All those different types. And then, of course, there's Racket, and now there's going to be Rhombus. So lots of different, and then, of course, there are lots of implementations of Scheme for any given version, like R6RS. There are a number of implementations. So maybe I'll talk a little bit about that. Okay. Just to, it's hard to know what I can leave out. But that's somewhere I feel like if I'm going to talk about Scheme, I should say something about it, because otherwise people are going to say, well, what in the world's R6RS? Or, your code runs under R6RS and I'm using R7RS small. Is that a problem? That type of thing is a reality. So those are kind of the differences between the nice, beautiful theory and then, how do I get my code to run on my laptop? Which version and implementations of Scheme are we using and why? Well, we're going to use Scheme, which is an implementation of R6RS, and then we're going to use Racket. Okay, why are we going to use those? One of the reasons I'm saying these things, by the way, is so I can listen to this video later if I want. But for these things, I'll just fill this in. I really want to get to examples, but I do want to get through the, just kind of go through the order and make sure it makes sense. The reason we're going to use those versions, well, Scheme is very efficient. Implementation has good memory usage. It's very mature, and it's fast. So that's good if you're doing things like program synthesis. And I just know Scheme very well. Racket, easy to install, lots of features. Racket is now built on top of Scheme and has very powerful macro system, commonly used. Some nice things there. Has pretty nice to use IDE with some nice features. What we need to know about Scheme and when. Okay, this part I'll have to kind of fill in. It's like, what was the point of this subsection? I think, I guess part of the point is, if you look at like R6RS, there's actually quite a bit you could know. And there's a lot to know about things like, the libraries and, continuations, macro system. There are some fairly advanced language features, but we're not going to use much of that. We're actually going to try to keep it to a very small subset of Scheme. So this is where I could talk about that a little bit. I don't know. Some of these subsections maybe get merged or whatever. I'm just trying to put placeholders for what I might want to talk about. Useful Scheme resources. Okay, things like Kent Divig's the Scheme programming language, 4th edition, which is available online. That's a great resource. It's probably my favorite resource. And then, there's also the Scheme manual, which is online. And they're cross-referenced, cross-linked to each other. So those are great resources. And of course, there's lots of books on learning Scheme and learning interpreters from Scheme and all those sorts of things. Essentials of programming languages, structure, interpretation of computer programs, all that. Lots of books. Okay. Pretest. So this is where the pretest goes. The pretest for Scheme, so that the reader can see if they need to read any of this. Okay. I'm just trying to make it accessible to people, so they don't, like I always find it kind of daunting. I want to learn some topic, like in this case, relational interpreters. And it's like, oh, well, that seems interesting. I want to get into it. And then there's like chapters of background material on scheme and on miniKanren. And it's like, well, can I skip that safely? Is that okay to skip it? Or I think I know some of that. Is that all right? Do I know enough? So the idea here is have the pretest, and I don't know how to write the pretest yet because I'm not exactly sure what's going to, we have to write the rest of it. But I would like to have a pretest where someone can, sort of check their own knowledge, like, hey, do they know what these things are? And if they can do well on that, then yeah, they can skip ahead. And if not, here are the subsections where we talk about that, and you maybe want to have a refresher. So, I think that's a reasonable idea. Yeah. Anyway, that's something I'd like to have. There's always this tension between cutting everything out that's not absolutely essential, and just like going directly to, say, relational interpreters, and also the fact that, well, there are a lot of people in the world who could easily understand this material, but they just don't know scheme, and they don't necessarily want to go out and read a bunch of books on scheme in order to understand the ideas of relational interpreters, which really have nothing to do with scheme. It's got nothing at all to do with scheme, really. You could do it just as well in another language. It's just, but we have to have some language for discourse. So, yeah. Anyway, so the pretest, maybe we'll keep that. We'll see how that turns out. All right, now we're getting into it. Literals, numbers, and numerals, booleans, and truthiness. Okay, type predicates and procedure application. Number question mark, boolean question mark, expressions and values. Okay. So here's what I think I'm going to do. I like that advice of always starting, never starting in the beginning. Start like somewhere in the middle or something like that, where I have some idea of what I want to say. So let's do that. Let's start in the middle. Okay, and here's also another thing. If we're going to talk about things like numbers, I think we want to typeset that a little bit. We'll say that's verbatim. Oh, sorry, yeah, like these, the scheme stuff should be typeset. 0 question mark, typeset and verbatim. Yeah. We'll go back to that in a minute. Symbol question mark. Okay, list. List question mark. Empty list, quoted, null. Ooh. Okay. Cons, pair question mark. Variable reference, procedure question mark. Variable reference to procedures, equal, EQ question mark, equal question mark, or huh. Okay. Sometimes I'm using text TT, sometimes I'm using /verb. I think maybe you have to protect the verb in the section headings. Let's see. Eval usage, REPL usage. Okay. Just trying to typeset that a little bit more nicely. So let's see if it makes. Okay. looks better. Interp.tech, got it. Git commit, writing. This is in my personal GitHub repo, which is private, at least for now. But I'll move over the files, like the LaTeX files and the PDF and the Markdown, to the public repo when I'm done with the session. Like I said in the last video, I just, there are certain notes and things like that, like when I push, how often I push, all that stuff gets weird to me, like having all that public. So I'm certainly happy to share what I'm writing. Okay, so it's like mostly open. And of course, these videos make it more open. Alrighty. Now I just want to see something here for the type setting. So TextTT. There's this issue of typesetting that it's kind of annoying. All right, so here we have expressions and values, and then we have a section on if. Now I think if I do /verb, if I remember correctly, having verb around if in a section heading causes trouble. Yeah, here's an error. Okay, so it didn't like that. Verb illegal in argument. All right, so do I have to protect it? /protect. Stupid LaTeX stuff. Let's see if that works. Make squeaky, and then make squeaky cleans all the files. Okay, that also looks like an error. That didn't seem to work. Just try something else. Try changing to the brackets. Also is an error. Okay, well, TextTT it is. Okay, if all right, and I wanted to typeset. So I'm doing pretty lightweight typesetting here, in my opinion. Quote of datum goes to datum. All right, how do I want to do this? Could use Alt-T. How do I want datum to look like? Well, let me just do this for now. I'll just typeset all this in verbatim. The datum arguably shouldn't be typeset in verbatim. I have to decide what convention I want, but for now I just leave it like that. Okay, so I think it's all typeset in terms of, this is code or whatever. Okay. All right. That looks good. Let me just commit that and push it. I tend to commit and push a lot, especially when I'm doing stuff like this. I just don't want to waste a lot of time uncovering LaTeX errors, because I made a little fiddly LaTeX mistake 10 minutes ago. Now I spend an hour debugging it. Okay. And also just, I guess it flushes my brain buffer or something. Like, it's like, okay, well now it's like having a dirty flag on an editor. You just haven't saved it. It's like, well, there's like a little nagging thing. I haven't checked it in yet. So, okay, so where are we going to start? I think maybe comments are okay. Where do I want to start? Quote, lists. I don't even have to write text. I can start like writing examples. I find if I write examples, the text often comes. So let's just speed run it. Numbers and numerals. So we have 5, 42, 0. We will restrict ourselves to non-negative integers. Now, from a typesetting standpoint, what we type in for scheme or at the REPL, when we type in 5, that's like not the platonic number 5. That's a, some representation of a numeral. Okay, so there's a difference between numerals and numbers. That's something Oleg taught me. The platonic number 5 can be represented as the Arabic numeral five, the Roman numeral V. Suppose I could do like the Japanese kanji for go. It's like, I don't know if I have the, I'm gonna keep that. So that's the sort of thing that would be cute, but I need to make sure that I can like typeset it properly. Okay. Okay, so how else can you represent it? We call it when it's like the unary numeral 11111. Okay, we could do binary. Okay, that's probably enough. So that distinction, this distinction between number and numeral appears when we use piano representation in scheme or miniKanren. When we use piano numerals, where we might represent the number 0, so actually let me put, say, the Platonic number 5 like that. Number 0 as the scheme symbol. Now, so I haven't introduced symbols yet. So this is already like an issue. The number 1 as the scheme list Yeah, there are lots of ways we can represent the successor. Where the symbol S stands for successor. The number 2 is the scheme list so let's see. So I guess this would be using it this way. So we're not using dotted pairs explicitly. It would just be like that, and you'd see this. Okay. And so forth. Okay. Yeah, I don't know if I even want to The thing is, this isn't so much about scheme. This is like sort of a conceptual difference between the idea of a numeral and the idea of a number. I don't think I want to talk about this because it has nothing to do with scheme. So I am going to move this to my new attic. All right. Yeah, I'll keep it around. Maybe I'll use it at some point, but that's not something I need to talk about now. Okay. Okay. So I don't think I need to talk about numerals. I'll just talk about numbers. Okay, so here we're talking about literals. So one of the things I have to talk about is the difference between an expression and a value. And like literals, we have these self-evaluating literals. So 5 evaluates to 5 in Scheme. You don't have to quote it, for example. Same with Booleans. It's actually the beginning I find is really tricky to get all this exactly right. Scheme has 2 Boolean literals that represent okay, I'll do it this way. Blank -f, which represents false. Now here's the sort of thing where grammatically that comma should go inside of those quotes. However, that can cause trouble later when we're dealing with code. So it's the sort of thing where it's like, yeah, grammatically, like you're supposed to do it that way, but that's not necessarily a good idea to do it that way. So I will not do it that way. And #t, in fact, I'll get rid of this comma, #f representing, okay, representing false, and #t representing true. In fact, any value. So here we have the concept of value. Any value in Scheme other than #f is considered a true value. I don't like the in fact there, but anyway, other than, whoops. Okay, that's an old habit. Maybe I should add a Scheme macro. In fact, any value in Scheme other than #f is considered a true value. For example, five and 0 are considered true values. Both 5 and 0. True values in Scheme. Do I have to use the word value? So tricky to introduce these technical terms. I mean, value is a technical term. In fact, I could use object, but that's a technical term as well. Scheme has 2 Boolean literals, #f representing false and #t representing true. #t is not the only true value in Scheme. In fact, any value in scheme other than hash f is considered a true value, is considered true. For example, both 5 and 0 are considered true values in scheme. Okay, so maybe I don't want to talk about that part until I get to if. Let's move it to if. And then if I want, I can have a forward reference. So if's coming up pretty quickly. Okay. Type predicates. Okay, so that's fine. See what a literal is. So do I want to get into self-evaluating literals? Do I want, I mean, I think technically these are literals. I could look at the scheme spec, scheme report. To do, say what a literal is, numbers we restrict ourselves to non-negative integers. In this book, we will restrict ourselves. I think that's true. I don't think we have anything that's not a non-negative integer. In this book, we restrict ourselves to non-negative integers. And we can have some sort of big num. Okay. It's fine. Booleans and truthiness. Scheme has, I don't want to talk about the truthiness, I guess. Boolean literals. These are numeric literals, Boolean literals. Do I want to say it that way? And just numbers and Booleans. Okay. Type predicates and procedure applications. All right, so the idea here is I want to talk about procedure. Okay, so I want to do something like use a call. All right, this is where I can start having examples. So we can use number question mark of 5, and that evaluates to hash t. Okay, that's great. And we can also ask number question mark of hash t, and that gives us hash f. Okay, so those are two fine examples. I'll be lazy right now and wrap verbatims around, or verbs around all those. Okay. Now that requires we have the notion of a procedure application. So we can have a type predicate. And so we need to know what a predicate is. In scheme, we need to know this convention about the question mark. Convention. Okay. Predicate. always terminates, and so it always terminates and without, I think that's true. It always terminates without an error. Terminates, it always terminates without producing an error. And always returns one of the two Boolean literals. Hash-f or hash t. So if you have a procedure that could go in an infinite loop, or could give you an error, or could return anything other than hash t or hash f in scheme, that's not considered a predicate. At least that's Dan Friedman's view. I think that's right. I think that's the scheme philosophy. So that's certainly how I understand it. Yeah. We have a convention where predicates, by convention, the names of scheme predicates end with a question mark. Okay. It is a scheme convention to end the names of predicates with a question mark. Okay. Also by convention, many people. Okay, so this convention thing we can put here, I guess. Okay. Okay, we haven't talked about procedures yet. Scheme predicate a predicate in scheme, a predicate is a procedure that, when called, always terminates without producing an error, without signaling an error, I think is the technical term still, without signaling an error, and which always returns one of the two Boolean literals, hash f or hash t. Okay, so I haven't talked about procedures or calling procedures yet. All right, we haven't talked about type predicates either. Type predicate is a predicate that can be used to determine the type of a value. Ugh, or do we say object or what? Oh. Okay, so these are technical. Actually, that shouldn't be a verb. That should be an inf. This is a technical term that we're defining. A predicate is a procedure that, when called, always terminates without signaling an error, and which always, it's a procedure that always, and that always, and that procedure which procedure. Okay, I'm just going to say, and that always call return blah blah blah. It's pretty tricky to get all the concepts in the right order. A type predicate is a predicate that can be used to determine the type of a value. Okay, so we haven't talked about values yet. Maybe I just need to be upfront and say, oh, so if I'm going to have literals, maybe I don't introduce this concept of literals up front. Maybe I just say, maybe that comes later. I really put that section because literals like numbers and booleans go together in a sense. They're self-evaluating. Do I talk about literals and values? So a number is a value, a boolean's a value. We haven't seen anything that's not a value yet. Let me get rid of the literals right now. I can always add that back if that makes sense. These are now sections. Numbers. In this book, we restrict ourselves to non-negative integers. We restrict ourselves to non-negative integers. 5, 42, 0, whatever. Which may be of any size. For example, 5, 42 are all so what are those? Oh, so tricky to actually explain what things are. Okay, let me just leave it at that. Okay, numbers, booleans. Scheme has I'm going to try to write it very carefully. In scheme, the boolean hash f, get rid of the literal, represents false, while the boolean hash t represents true. Okay. Haven't talked about values or literals or any of that stuff. Okay. So the thing is, 5 is both, so 5 is an expression that evaluates the value 5. So we can't really talk about the distinction between expressions and values until we get to sort of compound expressions, or to some sort of expression that doesn't evaluate to itself, like lambda, actually, things like that. Okay, booleans, type predicates. Now a type predicate that's already defined, like number question mark. So that's a, if we have a variable, a reference to that variable evaluates to the procedure that number question mark's bound to. So that's not self-evaluating. So I could just say that there are these things called procedures, and then, okay, so that'd be a variable. Okay, so the issue is we have to get into variable reference to even talk about application. Maybe I should just go ahead and show like define here, and then get into variable reference. It's tricky to get the order right. If you read a book that makes this look really simple and obvious, then either they're pulling the wool over your eyes, or there was a great deal of care taken to do it right. Okay, so here we have define and we have variable reference. Let's try moving that up. I just want to introduce the ideas as needed in the right order, and to get into things like predicates and procedures and applications, that's actually quite tricky and subtle. Okay, so here we have, forget the pretest. All right, here's the begin detailed scheme description. I'll just put this comment so I can help me find this. Okay. Numbers. I mean, there's an awful lot to say about numbers, but I don't want to say much. Non-negative integers. This is like Dan Friedman style. Then we got big nums, booleans. Okay, and scheme the boolean. Scheme the boolean hash f represents false, while the boolean do I need to say they're booleans? Section's called booleans. In scheme, the boolean hash f. Okay, that's okay, because that I'd rather call it a boolean than call it a value or an expression or a literal or self-evaluating literal. Okay, that's fine. Define and variable. Okay, so this is okay because define is a special form. It's not an application. So we don't have to get into the application rules to show this example. And scheme define can be used to give a name to a value. Ooh, we have value. I mean, I could say 5 is a value, but 5 is also an expression. It's self-evaluating. Okay. So 5 evaluates to 5. For example, gives the name X to 5. Okay. I had to use the word value. Okay, how can I rewrite that to get rid of it? I could say something like, we can use define to give, I could say to give a name to a number or to a Boolean. Or I could say something like, we can use define to give a name to the number 5. Maybe that's a good way to say it. And here, by the way, I don't really need to say in scheme because this whole thing's on scheme. The Boolean, okay. We can use define to give a name to the number 5. Now I'm talking about numbers versus numerals. It's really the number 5 that we're representing. It's like a philosophical conundrum every time I write a sentence like this. For example, define x5 gives the name to a number. We get to give names to things. Maybe just say something like that. For example, define x5 gives the name x to 5. I could just say name things. To name things. So now I'm using things as like a loose technical term. To name numbers or booleans, I could say that. For example, define x5. While define Cats are cool. Okay. Gives the name, cats are cool, to hash a t. Okay. Okay, do I want to get into what is a legal variable name? Gonna skip that. Let me point. I think it's user's guide. Add full references and URLs. Okay. Can point to the relevant sections as I describe aspects of scheme. That could be handy. So here, if I want to talk about what names are allowed, like I don't really want to get into that. I mean, I could do a short version, or I could just point them. I'm just going to punt. It's like, here are examples. Cats are cool. All right. So now, so do I come clean and say that X and cats are cool are variables? Do I talk about identifiers, variable reference? Expressions, values, and statements. All right, I should double check this, but I believe that definition is a statement. Percent. It's basically it's used for effect and doesn't produce a value. In fact, you can't even use it in value context, expression context. Well, actually, I have to be careful with what I say. Let nil. Find x5, so that's fine. And that's in definition context there. So we can do that. That's perfectly fine. But if we do that, that is not perfectly fine, even though there's an implicit begin. Same with begin, explicit begin. Do I need to talk about begin? Maybe I do. Do I need to talk about these contexts? Can I hold off on that a little bit longer? Can I get to like if? I think if makes it really clear. But to talk about if, I have to talk about the parts of if, and that gets into like expressions. Maybe I need to talk about these things here. Okay. The expression x evaluates to the value 5. Which is a number. The expression cats are cool evaluates to, so this is that's true when it's a variable reference to the value hash t, which is a Boolean. Which is a variable reference Do we have any other types of expressions we can show at this point? In Scheme, we are primarily concerned Scheme is primarily concerned with expressions and value, it's have met 3 don't know how to say that. We need some sort of introduction. Intro sentence goes here. About scheme and expressions, values, and statements. Can add footnote or aside or parenthetical maybe. I guess I could end up with side notes at some point, but let's just say footnote or parenthetical about how in miniKanren we will also have the notion of terms, which generalizes the notion of values of a value. Okay. And the reason is that a term is basically a value that can also either be or can contain a logic variable. Okay, so we need something like that there. I'd like some sort of compound expression that's not just like a variable reference. And then we also have this notion of evaluation. Okay. Let's see if I can get away with this. The expression x evaluates, there's like three things here in the sentence, to the value. It's getting complicated. That's a hard sentence to understand. There's 1, 2, 3, 4, 5 pieces of typesetting and 2 parentheticals. That's a lot. Okay. All right, maybe that can be broken down to parts. And I do like, I want to have compound expression ideally. Okay, and then there's the idea of self-evaluating literal. So like 5 itself is an expression that evaluates to the number, like the value 5. How do we talk about that? I guess we could have quote and symbols. Okay, because that doesn't get into application. We could do that before we even got into variable references and define. Kind of like that idea. And then we can get in expressions, values, and statements. Okay, so let's try to get in. Okay, expressions and values are gone. Comments, converse, quote. Okay, here we go. Yeah. Symbol question mark is going to be a type predicate. So where's our type predicates? Oh, type predicates. Okay. So let's move symbol question mark to type predicates. Okay, and we're going to have quote and symbols. Great. All right. So we have numbers, booleans. Okay, now we have quote. So that now we have this nice compound expression. And quote itself is syntax. All right, let's just write a sentence. In addition to numbers and booleans, scheme has symbols. Which can be used to represent concepts. Abstract concepts, symbolic can be used to represent abstract concepts, concrete concepts. Can be used to represent all sorts of things. Scheme has symbols which are often used to represent, which are often used to represent concepts. I don't really want to get into everything they're used for, which are often used to represent concepts. Often used to represent concepts. For example, maybe we don't need for example. We can just do, no, I'm unplugged. All right, don't run out, battery. I mean, there are also strings, although we don't really use strings. What do I want to say? So what's a good example of a symbol? I could do like a chess piece, I guess, or something like that, although I don't think that's really the doesn't necessarily give the right idea conceptually. Could do something like green. Could represent something really abstract like love. Which are often used to represent concepts. Or symbolic data. I mean, really, it would be like a calculus formula or code or something like that. All right, let me rewrite this sentence a little bit. Scheme can represent symbolic information, symbolic data, concepts, abstract concepts, and symbolic data using symbols. Sometimes called quoted symbols. Okay, I guess this can get into the expressions and values right away if we want. If we want to create a symbol to represent the abstract concept of love. Should that be double quoted? Oops. Yeah, do my comma outside. We can write the scheme expression quote love which evaluates to the symbol love. I might break this up more. Let's do it this way. Produces the symbol. All right. A shorthand way because symbols are used so often in Scheme, a shorthand way there is a shorthand way to write because symbols are used so often in Scheme. Because symbols are used so often in Scheme, there's a shorthand way to write. Because symbols are used so often, Scheme provides a shorthand. Because symbols are used so often in Scheme, the shorthand notation can be used the shorthand notion, quote love, can also be used to produce the symbol love. Okay. It's equivalent. Is syntactically equivalent. It's actually like a reader macro, although Scheme doesn't have user level reader macros. It expands to the other. It's one way to think about it. I guess I don't need to even say anymore. I can say the equivalence shorthand notation. I just don't want to get into some of that. Okay, so here it is true I want to talk about this datum thing. This more general property of quote. I want to include that for sure, but I want to get into the expressions and values. I don't want to get into statements yet. But, whoops. Okay, so let's do expressions and values. Okay, I want to include 5 and hash f. Okay, so something about self-evaluation. Literals. All right, so now I want to get more precise, or at least more, yeah, I want to start introducing real terminology having to do with expressions and values. All right, I don't need to get into some big thing about philosophically, you know, how Scheme is organized. I can just get into, I just mention that this is an expression. So expressions, values, and evaluation. Okay, so now we can get into those concepts, I think. In scheme terminology, well, quote love is an expression. Okay. The shorthand notation quote love is also an expression. Both of these expressions evaluate to the symbol love Wow, having an audience, including one that's not listening. I mean, I could delete this video and it would work just as well. That's really helping me. Now, if I were deleting these videos, maybe it would stop helping me. But thank you for listening or not listening. Okay, at least I can pretend I have an audience. Both of these expressions evaluate to the symbol love. Evaluate. Okay, in scheme terminology, quote love is an expression. The shorthand notation quote love is also an expression. The equivalent that almost feels like a parenthetical. Okay, both of these expressions evaluate to the symbol love, which is a value. In scheme, expressions evaluate to values unless an expression evaluates in scheme terminology, quote love is an expression. The equivalent shorthand notation quote love is also an expression. Both of these, that seems like I don't need. That seems like a distraction. I mean, it's true, but is that important? Quote love is an expression. Maybe it's okay. Both of these expressions evaluate to the symbol love. Okay, the thing that's a little complicated, I mean, they do evaluate to the same symbol in scheme. They evaluate, I mean, they're really kind of the same. I don't know if I want to get into talking about both of those. It brings up things that might be confusing. Let me comment that out. Let me try it. keep that here. I'll get rid of this. I'll just try writing it without. Let me introduce some critical scheme terminology, which we will use often throughout this book. We say that quote love, some critical terminology, some crucial, which we'll use throughout this book. The scheme expression, okay. In scheme terminology, quote love is an expression. In scheme, expressions evaluate to values. Expressions are evaluated to produce values. In this case, the expression evaluates to the value love, which is a symbol. In this case, the expression quote love evaluates. Okay. And then we can say the equivalent shorthand expression. The equivalent shorthand notation blank is also an expression. Let's see how that looks. The equivalent shorthand notation, quote love, is also an expression, and also, which also evaluates to the value love. True, but Seems like it's not worth it. Okay. Okay, so here can add a footnote. Yeah, don't need it yet. Quote love is an expression. In scheme terminology, quote love is an expression. In scheme, expressions are evaluated to produce values. In this case, the expression, or I could just say, for example, the expression quote love evaluates, I could just say in this case, I have 3 sentences beginning with, I could just get rid of the in scheme. Expressions are evaluated, so that's like passive. A scheme expression evaluates expressions are evaluated. In scheme, expressions are evaluated to produce values. I actually like that wording better. In this case, the expression quote love evaluates to the value love, which is a symbol. All symbols, all scheme symbols are values. Okay. That's true. Is that how I want to say it? I can say numbers and booleans. Numbers and the booleans #f and #t are also values. Okay, let's just be upfront. Okay. In scheme, numbers and booleans. I have to be careful when I say this about numbers. I don't know if that's strictly true of every number in scheme. For example, the scheme expression, this gets into the numeral thing also. Scheme has the concept of Scheme supports what are called self-evaluating literals. Which refers to really literal syntax. Oh, how do I want to say this? It's like when the value is represented as itself. How do you say that? I think maybe examples are better here. What did we have? We had 5, 4, 0, blah, blah. The numbers 5, 42, 0, and big num, along with the booleans and the booleans hash f and hash t, I guess I could just do it the other way. I could show that you could quote 5. Maybe that's the right way to say it. I think that's the way to show it. Okay. Okay, that's a better way of doing it. Just show quotes more general. All right, so we can put this in here, I think. All right, let's just see if we can typeset. We've added a lot. Oops. Looks good. Okay. Quote and symbols. All right, great. Great. I don't think we need to get into define and variables. Well, I guess we need to get variables before we talk about procedure application, but we don't have to do define, but it might be better to do define first. Okay, that ordering looks okay. Let's check this in. I think this is a good stopping point. Made some progress. Awesome. I will copy this over to the public repo. Great stopping point, I think, and thank you very much. Hope to see you again soon. Bye-bye.